Hello friends, welcome back. In this video lecture, I am going to explain to you different types of discrete time elementary signals. We had already seen the various types of continuous time elementary signals in the previous video lecture. So here we are going to list some of the you can say the discrete time elementary signals. So before that, actually some left out part of the first previous video lecture I would like to cover over here. So I'll just try to give you the various properties of the continuous time impulse function, because those are very important and it will be helpful in many of the examples. Just let me write that properties of continuous time impulse function. We list similar properties for the discrete time function as well. Well, first let us list for this continuous time impulse function. So use another color. So here the very first property is that if the integration is evaluated for that impulse function del of t, then as we have said that it has got unit area, so the area under and that del of t function will be equal to 1, because it is having 0 width and infinite height, so that will lead to unit area. Okay, similarly we have the second property. If there is a constant k multiplied with that impulse function, and if it is evaluated, then that will be equal to k. Then the third property is that del of t, if it is multiplied with any other signal x of t, in that case, so x of 0 magnitude only will be present, and that will get multiplied with the del of t. Other magnitude will get nullified, because del of t exists only at instant t equal to 0. So therefore the final multiplication will be only for t equal to 0th instant. So del of t is already at 0th instant, and x of t will be only considered at 0th instant, that is x of 0. So now similarly fourth is, if suppose the del of t is a shifted version. Okay, so instead of at 0, if it is at placed at some other instant t naught, and if it is multiplied by x into x of t, so where that del of t is defined, in this case it is defined at t naught. Therefore except for that instant t naught, on all the other instants the magnitude of del of t is 0. So therefore x of t will be only multiplied at instant t naught. Therefore what will be the final multiplication? X of t naught times del of t minus t naught. Okay, so that is fourth one. Fifth property is that if integration is evaluated for this product of x of t and del of t dt, now what we are going to get? So here obviously we are going to get x of 0, because already we have seen that for this it is going to be unit area. So unit area into x of 0, whatever magnitude x of 0 is having, that we will get. Okay, similarly if integration is evaluated on the shifted version of that del of t, that is del of t minus t naught into x of t dt, in that case obviously it is going to be x of t naught. So these are the 6 very important properties of the impulse function, so you need to remember that. Okay, so now I'm not going to write the list of the discrete time elementary signal, because it is the exactly same type of elementary signals that we have already written in the previous video lecture. You can just refer here. So exponential signal, sinusoidal signal, exponentially damped sinusoidal signal, then unit step function, unit impulse function, unit ramp function. So instead of here signal or function, it will be called as a sequence. Okay, so that will be only difference here. Okay, so let us just try to remember from this list and try to write the signals for discrete time. Okay, so therefore here, or else if you want I can just take this entire signals from here. Okay, so these are the types of elementary signals. So what we had in the previous video lecture. So here it is going to be a sequence. So instead of this function, it would be better to write as a sequence because it is just a set of magnitudes. So this can be just written as mid ramp signal. It can be called as a signal or sequence. Okay, but it cannot be called as a function. Okay, so now let us first write for the discrete time exponential signal or sequence. I'll write it. Okay, so here let us just write some lines to understand what exactly we are doing. A real exponential discrete time sequence is given by a real discrete time exponential sequence is given by x of n equal to c into alpha raised to n. Okay, where alpha is e raised to beta and c and beta are real constant. Here imaginary terms are not considered, only real terms. Okay, now here again depending upon whether the value of n is uh, or you can say the alpha value is whether it is less than 1 or greater than 1, we will have decaying type of sequence and growing type of sequence. So if suppose if alpha equals to 1, so it is an important point, if magnitude of alpha is less than 1, the signal decays exponentially. And if magnitude of alpha is greater than 1, the signal grows, the sequence grows exponentially. Okay, so here for alpha raised to alpha magnitude or magnitude of alpha less than 1, we can try to draw the sequence here. Okay, so just let me use another color. Okay, so here let us have the base axis to represent the time instant. So here 0th instant, 1, 2, 3. So it is not a continuous signal, so we need to specify the instants. Okay, so just some instants that we need to indicate on this axis to understand the magnitude will be available on these instants. So on it will be having n instants. Okay, so now it is a decaying signal. So at exactly see that n equal to 0. So here the signal is given by, I'll just try to write here, x of n is equals to c into alpha raised to n. So alpha is less than 1. So it means it is having a decimal value. So power to the decimal will be always reducing 1. Okay, so therefore here initially it will be when it is negative values of that alpha, in that case it will be having larger magnitude. So I'll just try to take this as the largest magnitude. Then as the time or the instance goes toward positive side, so here exactly at n equal to 0. Okay, so alpha raised to 0 will be 1. So 1 into c is c. So at rest other it will be a decreasing type of signal, and finally at n equal to infinity it is going to become 0. So that is a decaying signal. Okay, so this is for magnitude of alpha less than 1. If the magnitude of alpha is greater than 1, so in that case here it is going to be a different type of, you can say, sequence. That will be a exponentially growing sequence. Again I'll take 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, so on. Okay, so I'll start from minus 3 here, so it will be say smaller. As the time increases, the magnitude will also start increases. Time increases means for every next instant the magnitude will increase correspondingly. So here we will get growing function like this. Okay, so this is again magnitude at exactly instant n equal to 0. It will be c, because that signal x of n is c into alpha raised to n, and here we are particularly talking about alpha is positive value greater than 1. Okay, so this is what we are going to get for greater than 1 value of alpha. Okay, so this is about the exponential discrete time sequence. Second one is a discrete time sinusoidal sequence. It is given by x of n equal to a cos of, similar to that continuous time expression only we will get. Only here instead of t we will be seeing n, and that omega, regular omega, is now replaced by some another type of symbol omega, so plus pi as it is. Okay, so again here a represents amplitude or maximum value of the signal x of n. Omega naught is angular frequency, then there is pi phase angle, and if this particular signal needs to be drawn, then this signal will look like this somewhat. Okay, so this is the representation of that discrete time sinusoidal signal. So you can see that the shape is sinusoidal, but instead of continuous values we have only discrete magnitudes at selected instants. Okay, so for example I have taken instant 1, 2, 3, so on, but it will be different, you can say, values, discrete values with uniform gap or uniform difference between two consecutive instants. So next one is exponentially damped sinusoidal signal. Signal or sequence also we can write. So here instead of drawing drawing that signals, I can just try to give you the representation. It is given as x of n equal to, so exponential term in discrete time is c into alpha raised to n sine of omega naught. And so here the signal will be damped, so you can imagine that magnitude of the values will be damping, so that let me just try to draw it only so that the things will not be doubtful. So let me just take that reference. So suppose the signal is like this, so it is going to reduce continuously after that instant. So here the magnitude will be okay. So you can just try to make out the shape here. So for every instant the magnitude is going on decreasing, so that is exponentially damped sinusoidal signal. So this signal x of n will be written as c into alpha raised to n sine of omega naught n. So here when it will be damped, when alpha magnitude alpha is less than 1. So this is the condition required for obtaining this type of exponentially damped sinusoidal signal. Okay, so next fourth one is the unit step function or unit step signal here. Unit step sequence, in case of discrete time we will call it as unit step sequence, and it is represented as u of n. Okay, and it is defined as u of n equal to 1 for n greater than or equal to 0, and it is equal to 0 for n less than 0. It means what? The magnitude of this signal will be available only after the instant 0 and thereafter on the other instants, but not for negative instants. Okay, so this will continue so on. This all magnitude is unity here. Okay, so this is called as unit step sequence. So it will be having magnitude equal to 1 for discrete instants after positive value of after 0th instant, or 0 n equal to 0, and thereafter every other positive value of n. Okay, now fifth type of signal, discrete time elementary signal, is unit impulse sequence. Okay, so unit impulse sequence is represented as del of n, and it is given as, mathematically it is given as del of n will be equal to 1 at n equal to 0, and del of n equal to 0 for n not equal to 0. Only at instant n equal to 0 there will be magnitude of this signal, and that magnitude will be equal to 1. Okay, so that is called as unit impulse sequence. And all the other instant, negative instant as well as positive instant, the magnitude is 0 here. Okay, so this is what is the unit impulse sequence. Now there are some properties of unit impulse sequence also, which will be helpful while solving many examples. So let me just write properties of unit impulse sequence. Unit impulse sequence. So the first property is del of n into x of n, del of n into x of n. So when del of n is multiplied with another signal x of n, so as the magnitude of del of n is available only at instant 0, so only the magnitude of x of n at instant 0 will be multiplied, other magnitude will become automatically 0. So we can write it as x of 0 into del of n. Okay, the second property is that if the shifted signal is multiplied, then obviously the del of n is now available at n naught, therefore the magnitude at n equal to n naught for x of n will be multiplied with the magnitude of the impulse function at n minus n naught instant. Then similarly, if there is a summation between minus infinity to plus infinity for del of n, as it is having only one magnitude, so it will be equal to 1 only. Then fourth property is that if summation is obtained between n equal to n to infinity del of n x of n, in that case it will be equal to x of n value, because del of n in that case is 1. Similarly, if summation del of n minus n naught into x of n is done, in that case we will get x of n naught. Okay, then sixth property is that unit step sequence u of n can be obtained by adding and shifting the del of n, that is del of n minus 1 plus del of n minus 2 plus so on. We can keep on doing this till del of till infinity. So likewise here we can totally convert this into a single summation starting from say k equal to 0 to infinity del of n minus k. Okay, now the final type of unit this discrete time elementary signal is the sixth one, which is unit ramp sequence. Unit ramp sequence. Okay, so it is defined as x of n equal to n for n greater than or equal to 0, and this is equal to 0 for n less than 0. Therefore if I plot this signal, so what I am going to get here is, so for negative instance the magnitude will be 0, but for positive instance, here for negative instance it is 0, because for n less than 0 here it is n, so for n less than 0 means negative instant, so magnitude is 0. But from 0th instant onward the magnitude will be equal to the instant itself. So that means at n equal to 0 magnitude is 0, at n equal to 1 magnitude will be 1, at n equal to 2 magnitude will be to add n equal to 3, magnitude will become 3. Add n equal to 4, the magnitude will become 4. At 5, 5. So this will continue. This is called as unit ramp signal, and this is represented as x of n equal to, or instead of writing this x of n, now we can write r for this particular term here. Here also we can replace this as r for ramp. Okay, r of n. So now this is about the different types of elementary signals. We have covered both the continuous time and discrete time elementary signals. So next video lecture will be on the operations performed on the signals. Okay, so till then, happy learning and thank you.